Since electric particles release electromagnetic radiation when they accelerate, they will consume energy by releasing radiation during free fall, and their falling speed will be slower. This seems to contradict Galileo's discovery. Later, Einstein proposed the general theory of relativity. One of the cores of this theory is the principle of isotropy. He pointed out that in a local area, without a reference system, it is impossible to distinguish whether an object is in free fall or floating in space. Just like the gravitational acceleration on the surface of a planet and on a flying rocket is the same. If the falling electric charge will generate radiation, but the electric charge in space will not, the equivalence principle will be broken. More interestingly, in order to balance the equivalence principle, a paradox will be triggered. If the electric charge in space is actually in an inertial system and should not emit radiation, then the electric charge at rest on the surface is actually accelerating and emitting radiation. This is the charge-radiation paradox in the gravitational field. First of all, the fact that accelerated electric charges release radiation is derived from the Larmor formula, in which only the electric charges are accelerated, but not the electric field. Just like the magnetic force of the land will only act on the particles themselves, but not on the electric field. The relative acceleration between the particles and the field will produce electromagnetic radiation. If the electric field is also affected by the gravitational field, there will be no relative acceleration. However, the support force on the surface of the electric charge does not act on the electric field, so the electric field will pass through the ground under the influence of the gravitational field, causing relative acceleration and thus radiation. Things get weird again. According to the Michael thought equations, if there is no current passing through the stationary charge and the electric field's strength does not change with time, the charge will not produce radiation. But if the observer sees that the stationary charge on the surface of the Earth produces radiation during the free fall, in short, for different observers, the relatively stationary charge will not release radiation. Which one is correct? The charge-radiation paradox in the gravitational field is still a theoretical dispute. So can it be verified by experiment? If we bring the gravitational acceleration into the Larmor formula, we will find that the radiation energy it releases is negligible. We need 5 times 10 to the 52nd power of charge to get 1 watt of radiation. It is estimated that there are only about 54 cubic atoms on the Earth. You can imagine how difficult it is to conduct such an experiment on the Earth. Not to mention, with so many electrons, gravity is almost negligible compared to the electrostatic force generated by the force field.